So now that we have looked at the broad contours of our overall solution, let's focus on the details. So the details are like this. So you can go to this ARC x86 entry 64 assembly file, because the moment we are looking at system calls or interrupts, these are coded in assembly. And the first thing obviously is to store the state of the program that was just interrupted. So interrupts and system calls are different entry points, but we'll focus on system calls, and interrupts are more or less a similar logic. The differences will be pointed out, but our focus will be primarily on system calls. So there is an entry syscall 64 function, which is kind of the only entry point for system calls. And this is registered, with the hardware in a hardware table. So the moment that, you have a system call, which is an interrupting instruction, the hardware knows which function to call, right? The hardware knows this. So you will see the sim code start directive in the kernel, which essentially says that this function is written in assembly language. And here, very carefully, the entire state is saved. So it's kind of a very, very nice and accurately choreographed set of actions where you clearly can't go wrong. And there is a precise sequence in which everything is stored. So even no two steps in that can be interchanged, because then the entire sequence will be wrong and then your context will not be saved correctly. So broadly speaking, these are the steps for saving the context after a system call. So the hardware will store the PC to RCX, the instruction pointer, and it will store the flags in R11, and this is done automatically. All right. The reason it is done automatically is because this cannot be done in code. If you do in code, you have to change the program counter, right? To run the code whose job is to store, but then whose program counter will it store? So the hardware has to do this. Whenever there is a system call, the hardware has to do it. Of course, here the assumption is that prior to executing a system call, you do not have anything of value in RCX and R11. That is what you're assuming, which means that your library has to clear up RCX and R11. If there is an interrupt, and an interrupt can come at any point of time, then you clearly cannot keep RCX and R11 free, right? Because keeping them free is a planned activity, but an interrupt is an unplanned activity. Then you'll have model-specific registers, internal privilege registers, and dedicated memory areas, where again the value of the instruction pointer, the code segment register, and the flags are stored. So in this case, as I said, there are several options. Either store it in a model-specific register, store it in a dedicated memory area, or store it somewhere else. So what happens in this case is that these three important pieces of information actually get pushed onto the stack by the hardware. So the hardware automatically pushes them onto the stack. It accesses the stack pointer, pushes them to the stack. Then what we do is that we store the value of the GS segment register. So the GS segment register actually swaps its contents with a dedicated model-specific register, a privilege register. So it's a way of storing it, basically, that whatever is there in GS, we store it in a model-specific register. And the stack pointer and few of the other things are stored in a separate segment, right? So as I said, we have segmented memory in x86. So x86 has a separate segment just for storing information related to the current task. Previously, it was used a lot. Nowadays, it is not used that much. But still, it is used for some things. The most important thing is the stack pointer. All right? Because before loading the kernel stack, you'll have to store the existing stack pointer somewhere. And because, as you can see, all of these things are being pushed to the stack, right? Fair enough. Even this is going to a model-specific register, but now where do you store the stack pointer? Because unless you store the stack pointer, how will you retrieve these things? That is why this is stored in a separate dedicated hardware segment known as TSS, which the Intel architecture provides. Subsequently, we set the stack to the kernel stack and do the rest of the context saving process. So the takeaway point here is that the hardware, in the case of a system call, will assume that RCX and R11 are free. So it will save the program counter and the flags into these two registers. Interrupts arrive unannounced. That is why these important pieces of information, namely these registers, are stored on the stack. Then the GS segment register in a model specific register. But now the question is, where do you store the stack pointer? So you store the stack pointer in another dedicated hardware area known as the TSS, which is called the task switch state segment. That is where your stack pointer is stored, in the TSS region, in the task state segment. So we will now look at the rest of the details, which is what happens when you load the kernel stack, because the rest of the context actually goes into the kernel stack. So in continuation, once the core part of the context is saved, then the data segment register, the stored stack pointer. So recall that the stack pointer is stored in the task state segment, TSS. And so the stored value is transferred to the kernel stack. And then in the case of a system call, R11 and RCX are important. So they are moved, and the code segment register, they are all moved to the kernel stack. So after this is done, so this is like some of the important pieces of the context that have to be done first. And once the program counter is stored, the stack pointer is stored. Of course, in this case, the stack pointer is coming via TSS into the kernel stack. And as I said, the reason for this is very clear, that if I overwrite the stack pointer with the contents of the kernel stack, then the stack pointer's previous value is gone. That is why you store it in a temporary place, which is a special segment. Then you reload the stack pointer. Overwrite the stack pointer with the kernel stack pointer. And then whatever you had stored earlier, you transfer that from TSS to the kernel stack. Once this is done, the rest of the general purpose registers can all be pushed onto the kernel stack. And in this entire process, the entire process is so sensitive that there is a need to actually disable interrupts during this process. Otherwise, what will happen is an interrupt will come, and then the interrupt handler will run, and then the entire state will get messed up. That is why in this critical part where states are being saved, there is a need to disable interrupts, and quickly once the state is saved, you enable them back again. And while restoring the context, you follow the reverse sequence of steps, which basically means that you start from here and you go back. All right, you start from here and you go back. Ultimately, the last step always is loading the value of the instruction pointer, which means that it goes back to exactly the point in the process that was interrupted. So essentially the next instruction, it is not the same point, but the next instruction. So this we have already discussed, where should you start, but wherever you should start, it goes to that point. And there is a mode switch. So if you are going to a user process, from kernel mode, go back to user mode. So the sysret and iret instructions precisely do that, which is the last stage of restoration. So in context restoration, sysret is basically the opposite of syscall. So syscall is a modern mechanism of making a system call, and returning from a system call is sysret. So in this case, what we do is, as I said, we do the reverse. So in the case of a system call, the RCX register stores the instruction pointer of where you need to go to. So that part, and the flags register is stored in R11. So that is also transferred. So there are many race conditions here that are possible if interrupts come, right, in the process of restoration. So let's look at them. So what happens is when you are restoring the state, that is not as critical as when you are collecting the state. Because when you're collecting the state has to be pristine. But when you're restoring the state is anyway there in the data structures, right? You don't have to worry that much. So let's say an interrupt arrives between setting the user stack and executing sysret. This is fine because the point is the interrupt handler anyway stores and restores the state. So this is absolutely fine. So the interrupt handler can execute. And because, this will also tell you why the interrupt handler needs to use a separate stack. Because when you are restoring, you are accessing the kernel stack. You don't want the interrupt handler to keep using the same stack. That is why you give the interrupt handler a separate stack. And any handler will return and restore the state that it began with. So in this case, even if you are the kernel and you are restoring the state of a user process, and then you jump to some sort of an interrupt handler, you come back here, and then ultimately you go to the user process. So this is fine. So there is no need for disabling and enabling interrupts, right, when you are actually restoring the state. Because also think about it another way. You will disable the interrupts when you are in kernel mode, but then you will go to user mode. When you will go to user mode, the user process cannot enable. Of course, you can say that the hardware will enable the moment you go there, like overloading the sysret instruction. But that, as we have discussed, is technically not needed. So you would not want to disable interrupts for a long duration because it makes the kernel less responsive. So in this case, there is no need. If you look at the iret instruction return instruction, then in this case, you are restoring the values of 3 pieces of information. RIP, which is the 64-bit instruction pointer. So you use sysret to return from a system call, and iret, the iret instruction, to return from an interrupt handler. So the restoration process is more or less similar, and you just need to bear in mind the system call is a planned activity, whereas an interrupt is an unplanned activity. So in this case, you restore the values of the instruction pointer, code segment register, and flags. Right? These are the things that you restore. And setting the value of the instruction pointer is equivalent to actually jumping to a point in the user program. So it is as if you are going to the user program and you are jumping to a point in there. So this completes the storing process and the restoration process. We have mostly discussed this in the context of a system call, but again, in the context of an interrupt, there are minor differences. We have covered that as well. So that is not very important. So broadly speaking, this is where we stand in terms of saving the context as well as restoration. There is a little bit of additional context, as we had discussed, which is stored in thread struct. For instance, the thread struct has a list of thread local storage regions. It could have the stack pointer in some implementations of the kernel. It has the segment register values, IO state, and so on. So those are also restored. But as I said, this varies with the architecture, right? So what it stores actually varies with the architecture, and it is not like a universal thing. So in any case, whatever is the state, everything is restored prior to switching to the user program. So once the context is saved, right? So as we have discussed, right? So we have discussed the saving process, the restoration process. So let us now discuss what exactly happens when you enter the kernel, because you're in the user mode, then you're in the kernel mode. So when you enter the kernel, we have already discussed that the context is safely stored where? On the kernel stack, and the context is also safely restored from the kernel stack. But in this process, it is important and necessary to take the help of other storage locations as well. For instance, the most critical things to actually store and restore are the instruction pointer, flags, and the stack pointer. They are like the primary citizens when it comes to restoration, saving, and restoration. So instruction pointer, So in some cases, if the code segment is changing, like in the case of an interrupt, the code segment register also, but let's treat it as a part of the instruction pointer logically. Then we have our flags and we have our stack pointer. So these three are our special citizens. So what we have seen is that the hardware in a user to kernel switch automatically puts it in a set of known registers because system call is a planned activity. In the case of an interrupt, which is an unplanned activity, the hardware puts it on the stack, which later on has to be retrieved. Then the stack pointer has to be stored in a temporary location because it is going to be overwritten. So on x86 machines, it is stored in the TSS segment, which is a special segment. And later on, you read it from there, and ultimately the entire context goes on to the kernel stack. And the entire context is restored from there. And even when the process of restoration, RSP, R flags, and RIP are special citizens. Once you are done with the kernel stack, you will restore the value of RSP. So RSP will now become the pointer to the user stack. But mind you, once the value of RSP points to the user stack, the kernel stack cannot be used again. It's gone, right? So RSP is pointing to the user stack. So the kernel stack cannot be used. So which is fine because by that time you have restored everything. So the final step is to restore RIP and R flags, which you can either put in two registers and then you can, they will be in two registers and then automatically your sysret instruction will take them from there. In the case of an interrupt, these would already have been pushed onto the user stack. So an interrupt return will actually fetch them from the user stack and start executing from there. So you can clearly see how both the mechanisms are working. In the case of a system call, which is a planned activity, you can afford some efficiency, right? And well, affording efficiency is not the right word, but you can have some more efficiency, which is you can use registers. Interrupts are an unplanned activity, which is fine. So in this case, of course, you can't keep registers free because you can never anticipate an interrupt. So that is why the RIP and R flags will actually get pushed onto the user stack. All right. That is all right. So when you are coming back, you set your last operation in the kernel will be to set the stack pointer to the user stack, and then you issue the iret instruction. It knows that the top two entries of the user stack are actually your RIP and R flags. It will pluck them out and it will jump. So this part is understood. What we have already discussed a few slides ago is that when you are moving from the user to the kernel, then there is no need to create a separate kernel thread. Right? There is absolutely no need to create a separate kernel thread. So the same thread can continue, albeit in kernel mode, and it can also, same thread can continue for interrupt processing as well. Now here is the thing. If you have gone to the kernel is an opportunistic customer. So the thing is, you got a system call, you got an interrupt, you went to the kernel. But there is no reason that the kernel is going to repay or return the favor. Because the fact is you have gone to the kernel. So the kernel will now basically see what is the best that it can do. It has many options. It can do some of its own work, which was pending. It can start a different kernel thread. It can start a different user process. It can resume the same user process. Or it can start a different thread in the same thread group. It can do anything that it wants. Right? Because it's a kernel and the kernel can do anything that it wants. So what it does is that the first is it sees if it has some idle additional work to do, which has a higher priority. Because as I said, you went to the kernel, now you are at the mercy of the kernel. So it calls the exit to user mode loop function if there is some work to be done. Other than resuming the user process, it actually calls the schedule function. The schedule function is where your scheduler runs. Its job is to find what is the next task that I should execute. All right. If there is a need to schedule. In this case, if it finds another task, it will call the context switch function. So the context switch function can either be for continuing the same process or maybe the new one. So as you have seen, if you have a new one, there is a cost, right? If it's a different user process, not in the thread group, then you will have to flush the TLB and load a new page table. So that is not desirable. But the kernel may say that, look, one process has been running on forever. So fairness is needed, right? Fairness is also important in a system. You can't continue to run the same process. So what the kernel does is that it calls the context switch function if it feels that there is other pending work of potentially a higher priority. So the run queue is a data structure. So actually the way the run queue is written in Linux and also in our book is that run and queue don't have a space. Here I've put a space because you're seeing it for the first time, so you should know what it is. But in the rest of the slides will not have a space. So the previous task is a task that was running. The next task is the one that the scheduler chose to run. So when you are doing a context switch, right? So now we are looking more at the process of restoration in deeper detail. Well, this is actually a context switch. You will prepare the task switch, which means that you will tell the previous task that so this is done only when previous and next are not the same. So you will tell the previous task that, look, you are not running anymore. All right. So its state can still be task running, but it will not run on the CPU, right? So it will not run anymore. And then you will do an architectural context switch, right? So you will initiate and initialize that process, but you will not do a full context switch because few more steps are remaining. So at the moment on x86, arc start context switch actually doesn't do much. Because so you need to understand, right? From the point of view of the kernel, the same set of functions have to work for every architecture. And as of today, Linux runs on everything. In fact, even if I am creating a new hardware, the only thing my customers will ask me is, does it boot Linux or not? That is the only criteria on which I am evaluated. So you can ask anybody who is building, for instance, new RISC-V hardware. So that person, even before you ask the person, he or she will tell you that we boot Linux. Right? That is like a certificate or stamp of authority that their processor is done. All right. So whatever steps you have, you will be kind of more liberal and you will have a lot of functions, but all of those functions will not be relevant for every architecture. But still, you want to create some sort of a superset. So in that case, you'll first prepare. So preparing is clear, telling the previous task that you are swapped out. Arc start context switches in case your architecture requires something to initiate this process. x86 doesn't require. The important thing is to switch the memory structures. So we will see there is a little bit of a issue here. And then switching the register state and stack, and finally finishing the task switch. Right, so the memory structure in this case will be this TLB page table business that we have been talking about. And then the register state and the stack is just the discussion that we finished, which is all the registers and stack pointers and so on. And finish task switch will either be iret or sysret, where you execute these instructions and finally you go back. Right, that is basically finish task switch. So we have broadly seen everything. What we will look at is switching the memory structures because that is the most important from our point of view. So let us understand what is going on. So what is going on is that we know that every task struct has an struct. This is something that we know, correct? That every task struct so a task struct is a task structure for a user process, for a kernel process, kernel thread, right? Everything. It has an element called which is an struct. So struct means struct star always, right? You never have a structure inside a structure, you always have a pointer, right? As is the norm in C. So this you have appreciated. So there is an and there is an active all right? So this and active they convey a very interesting story. So let us understand what they are. So if you would recall, when we were discussing task structs, we have said there is an active we'll discuss it later, and that later point is here in slide number 88. For a user process, is equal to active Both are the same, right? So in this case, both the pointers are the same. So I would just like to make one small digression. The kernel code, you want to minimize replication, you want to maximize efficiency. Hence, we always deal in terms of pointers. All right. So in this case, when I say struct is a pointer to an struct, and in this case, in the user process, and active are identical. If it is an exclusive kernel thread, right? It is not one of those user processes which got temporarily promoted to a kernel thread and you expect it to get demoted soon. It's not like that. But it's a regular kernel thread. Its will be null. Because all kernel threads share their virtual address space, right? Because they share a virtual address space, they don't need a separate struct. What do they need it for? Because struct's main job is what? To maintain a pointer to the page table. To basically have a list of all the virtual memory regions, so on and so forth. But that is anyway common for the kernel space system-wide, right? So you don't need a separate structure for every thread. That is why is null. But active is important. Active is actually the struct of the user process that executed the last. Right? So let's say you ran some user process and then you got an interrupt or an exception or a system call, you came into the kernel. It is possible that after that you kind of cycle through many kernel threads, but you would always like to have a pointer to the active of the user process that executed the last. Because maybe you are still servicing its system call. Maybe you need something from its address space. It is always good to have a pointer to the struct which wraps the page table and virtual memory regions of the user process that executed the last, right? Is that correct? On the current CPU, of course. So far, so well, not on the current CPU. I would like to kind of change that. It's basically in this current thread of execution. It's like, one kernel thread runs and then you run the schedule, you run something else, right? So it boils down to that, what I said, but it's better to explain it in the other way. So let us now look at the different cases and understand, right? So what you are seeing is actual kernel code, right? So I've cleaned it up slightly, but clean it up meaning I've not changed the sentence, I've not changed the statements. I've erased a couple of things which are not relevant to our discussion. If next is null, next means the task that you are switching to, that is null, which means you are switching to a pure kernel thread. Correct? That is what next means. Null means you are switching to a pure kernel thread. No problem. Then you set next active is equal to previous active which means that you will simply propagate the information of the last user process which was swapped out. That information you will simply propagate. So this is clear why you will propagate, because this is one information you always need to hold as an invariant, and your previous task knew something, so you will propagate that. In case you are getting into the kernel, the last one is a user process. For that also is equal to active so this information is propagated. Now let us see where are you coming from. You could either be coming from user space, or you could be coming from a pure kernel thread. So if you're coming from user space, prev.mm will not be equal to null. All right. So then that is fine. You simply increment the reference count of the struct of the user space to indicate that there is one more thread that is interested in it. The user process is already interested in its struct, but now the kernel thread is also interested in it. So you simply increment its reference count. So incrementing the reference count, the main advantage is that later on, as the user, you decide to kill it or something, you have a count of how many other processes have a pointer to it. Unless this is 0, you would not like to deallocate the structure. If you are coming from the kernel, means coming from a pure kernel thread, then you will come to the else part. So then the previous thread's active MM can now be null. What's the point of having it to be non-null? Because the previous thread has done its job, it has finished its execution. Now you are the new thread. So you clean up the state of the previous thread, right? There is no need for it to hold any state. So you set it to null, you do a cleanup operation and you move on. So let us now consider the other case. The other case is much simpler, that I'm switching back to user space. So I'm switching back to user space. What I do is that if I'm resuming the same process, nothing needs to be done. Else, I just call a function to load the new page table and flush the TLB because I'm resuming to a different user process. So you can look at the corresponding code in the kernel. So I'll provide a pointer to it, but the idea is very simple, that whenever there's a kernel to user transition, right? So look at the switch to function, the underscore. So I'll explain you the significance of underscore, but the idea is the same. You're going back to the same user process, all good. A different user process, which is not another thread in the thread group, then there is a need for a switch. So if the previous thread is an exclusive kernel thread, then of course set its active MM to null. This you have already seen on the previous slide. So what it does is it cleans up the state. So let us now understand this visibility business in C. The reason why this thought is coming to my mind is basically because of this underscore business. So see, C variables and function names can have underscores in them, absolutely legal. And they can even start with underscores. So having an underscore does not confer any special status on it, but there is a room for a convention. The convention is like this, that you need to understand that in a large program, I'm going to have a lot of variables, lot of functions, and so on. Global variables are in general a bad idea, right? You should never use global variables unless something is genuinely global, right? Something genuinely global could be like the name of the operating system, right? Everybody should say Linux, right? But genuinely global variables will be far and few. And if it is read-only, then make it a hash defined, make it a macro, right? Well, hash defined is not a macro, it's a preprocessor symbol. So you will, in general, not face the need to make any variable global. If at all, do it very sparingly, because having global variables in a large project is a very, very bad idea. Even a function, if you see, the function is also global, right? The entire world can see it. That's also not a good idea. Definitely not a good idea, because most functions do not require that level of visibility. If it was an object-oriented language, then I could always have the modifiers public, protected, and private. Private would be that the function is visible only to variables and functions within its class. Protected means its class and its derived classes. And public means the whole world. But that said and done, in general, variables themselves should not be public. Every variable should be protected with what is called a getter and setter method. In the sense, if the variable is x, then the getter method should be getx, the setter method should be setx, and x itself should either be private or should be protected, because you don't want variables to be accessed directly. It is very hard to sort of keep tabs on who's accessing the variable. If it's a function, it can very well be an inline function, so the compiler will optimize it. But at least you will know that who's accessing it, and later on, let's say you want to change the units of the variable or do something, anything, it is very easy to do that. Hence, wrapping every variable with a function is the way to go in a large multi-file project, right? Restricting access and not having things global is basically the right approach, right? Also, but the point is that these things are not there in C. So in C, what you have is that if you define a function as static, not a variable as static, a function as static. So you do static int something. Its visibility is restricted only to the C file that it is defined in. It is not visible to other C files. All right. And the convention that the Linux kernel follows is that if any function starts with underscore, you will see almost inevitably it is defined as static. Underscore functions are meant to be internal to the C file, not visible outside, but of course, prefixing it an underscore does not ensure that. But underscore, the name means it is internal, and they would have also written static to ensure that it is not visible outside the C file. The linker does not take cognizance of it. All right, so visibility is an important aspect in software design. So the switch to function that we are discussing basically will do some of this stuff, and it will also do more. It will extract the thread structures which have additional context. For example, the thread local state, the segment registers, all of those things will be switched. The current pointer, which points to the current task, that will be switched. And the rest, floating point state, ALU state, general purpose registers, model specific registers, everything will get switched as per the logic of the program, as per the sequence that we have seen. One sequence is followed while saving the context. Exactly the reverse set of steps are followed when restoring the context. Finally, we'll have finish task switch, which will set the status of the pref task to say you're not running and next task to running. And sometimes it would have so happened, right? So this is like right before you're doing the hardware switch. Sometimes it may so happen that the size of your kernel, the physical size of the kernel, is bigger than the virtual memory space that is allocated to it. That will not happen on 64-bit systems. It will happen on smaller systems, 32-bit, 16-bit. So on 32-bit systems, the kernel has 1 GB, but it's possible that you actually have more. So what you will then do is that you will have some part of the virtual address space and sort of create a kernel level swap space and bring in some pages here. And once you are done, essentially unmap them and throw them out. So something of this nature, so there is something called kmap which allows you to do this, where you are basically saying that my process will require some pages and they are not required by other processes. So those pages I'll bring into some region of my virtual address space using kmap. And when I'm leaving, I will do k unmap and essentially unmap them and go. So all of those things are done while wrapping up. And finally, you do the hardware level restore and you go out. So now our entire discussion on saving the context and restoring the context is done. We will have one slide on some interesting trivia, right? So whenever you see the burger like this, it's a good food for thought. So you'll often find statements of the form likely and unlikely, right? So you'll always find likely some sort of condition, then you do something, right? With an if statement. So likely and unlikely are basically hints that you are giving to the branch predictor in hardware that this branch over here will most likely always be taken, right? And similarly, this branch, it's always unlikely, right? So likely and unlikely are a way for the programmer to actually increase the efficiency of the branch predictor via compiler level hints. So at the moment, this is written like a macro, but this will translate to an instruction that provides a compiler level hint. It basically tells the branch predictor that this branch will go in a certain direction, either taken or not taken, because the branch predictor may not be so smart, but as a programmer, if you have the intelligence, why not convey that? That is one. So this is one way where the kernel code deliberately improves its efficiency by sort of directing the branch predictor that this is what you predict. The other is you'll have statements of the form latent entropy. So latent entropy, what this does is that, when you're running the kernel, a lot of things are happening, right? Hardware interrupts are coming, a lot of things are happening. So it's a reasonably complex, chaotic, and non-deterministic environment. So in that, what can happen is that you are allocating so many pointers, but next time you run the kernel, the values of those pointers will be different because the order of the instructions and a lot of other things will change. So the pointer that you get will actually be different because the memory allocator will allocate it differently, right? No two runs are the same. So the values of all the pointers of different data structures, you kind of combine them. It creates a source of randomness. All right. It may not be a very strong random number, but it's a reasonably strong random number, which in many cases is sufficient for cryptographic purposes. So you can use this as a random source to generate a cryptographic key. Because to generate a cryptographic key, you actually need a true random number generator. But unless you are using quantum phenomena and so on, it's very hard to create a true random number generator. But this is reasonably practically close to a true random number generator for practical purposes. No theoretical guarantees, can be broken, of course. But the thing is that in many situations, just extracting this information from the kernel can allow you to create a reasonably good random source. Hence, you will see the term latent entropy with many kernel functions. All right. So this clears and clarifies many of the doubts you would have while reading kernel code. So this is the end of this chapter. Always a good slide to be in. So if I were to just conclude and summarize what we have done in this chapter, if I actually go back to here, the roadmap, this one. So we have looked at the concept of processes. We have looked at the concept of the task struct. So this introduced the concept of the task struct. Then we looked at process creation, destruction, fork mechanism, right? The exec mechanism. Then we looked at process switching. Process switching, clearly we did spend a good amount of time on the TLB switch, TLB flushing, the page table, and also on the sequence of what exactly you store and how, right? So clearly in the sequence, the most important things are your instruction pointer, the flags, and the stat pointer. In the case of interrupts where you may be moving to a different code segment, the code segment register as well. And we also talked about system calls being a planned activity, interrupts being an unplanned activity, and how you store, how you restore. We looked at this process in some detail. So what we will do subsequently in the next chapter is look at the communication mechanisms between what you have just created and user level processes, because now we have created process, but they're not communicating. So we'll focus on how they communicate. There are 4 mechanisms which we'll look at. System calls, exceptions, interrupts, right? These are methods of getting into the kernel. And signals, which is a method by which the kernel sends a message to a user process. So I'll see you guys in chapter 4.